All right, we're going to be looking at solving absolute value inequalities today. But in order to be able to solve absolute value inequalities, we need to review compound inequalities. So some quick notes on things that I want you to remember. Remember when we're doing our inequalities, we're looking at these symbols. So let's say we're looking at less than and greater than. Remember that in interval notation, can't spell, interval notation, we use parentheses, right? Our parentheses, when we're looking at a number line or a graph, that's when there is an open circle. Right, some sort of open circle on a graph or a line, a number line. And this means that that value is not included in the answer. It's not a possible solution. And then when we have our inequalities less than or equal to or greater than or equal to in our inequality notation, our interval notation, we're going to have some sort of bracket, depending on if we have a closed circle on that value. So again, closed circle on some sort of graph or number line. That means that the number is included, or that value is included in the possible solution. So we're going to be looking at two different types of inequalities. We have what's called the OR type. In interval notation, we use this symbol that looks like a U. It's not you're not going to put a little curl underneath it. It looks like a U. We call this the union. So when we look at this linear inequality, we see that we have some sort of shading. We have a closed circle here. We have an open circle here. So if we write this out in inequality notation, we would say that my x's are going to be less than -4 because we're going to the left. So we would say our x's need to be less than or equal to -4 because we do include it. Or they can also be from 1 to positive infinity, or we're getting greater than 1. So x's are going to be greater than 1. We don't include the 1 because there's an open circle there. Now what I want you to kind of get used to seeing more and more is our answer in interval notation, and that's going to look like this. So we go from left to right. We know we're going from -infinity to -4. Remember that we don't ever include the -infinity, so there's our parenthesis, and we do include the 4. We can see it with this inequality right here. So we put a bracket. Then this is where that symbol of that U comes in. And then we go from 1, which we don't enclose, to positive infinity. And again, we don't include it, so we put a parenthesis. So we can go from interval to inequality and inequality to interval notation. Now to solve OR inequalities, we just solve each part, then graph on a number line to show the solution. So we're just going to graph each part, just two inequalities. And then remember, with our inequalities from before, anytime we multiply or divide both sides by negative, we need to flip that inequality symbol. So looking at this problem here, we're going to subtract 4 first from both sides. We're left with 3x is less than or equal to 6. Then we divide both sides by 3, and we get x equals 2. And then we have 5x is greater than 45, so we're just going to divide 5 right away. So my x is greater than 9. So on my number line, to show that my x's are less than or equal to 2, we're going to include the 2, so we do a closed circle. And then we just shade to the left because we want less than or equal to 2. And then our x's need to be greater than 9. So I'm going to do an open circle at 9 and then just kind of shade to the right. So that is on the number line. My interval notation, and a lot of times it's easier to look for your interval notation on the number line because I can read this from left to right. We know we're going from -infinity to 2, so that's going to be my first one. We have a closed circle at 2, so we put a bracket. And this is an or statement, so we use our union. And then we're going from 9, which we don't include, to positive infinity. And we don't include it. On this other one here, we have a less than or equal to and a greater than or equal to. So let's go ahead and solve this one. So I'm going to subtract 6 to both sides. We have n is less than or equal to -1. And over here, we're going to subtract 7. We're left with 9n is greater than 36. Divide both sides by 9. We get n is greater than 4. So again, when we shade here, we have -1. We want n's less than or equal to -1. So close circle at -1, and we shade to the left. And then my n's are also going to be greater than 4. So open circle at 4 and shade to the right. So my interval notation goes from -infinity to -1 included, in union with 4 not included, to positive infinity. Next, we have type 2. This is our and inequalities. I like to call this the sandwich inequalities. And the reason is we're looking at, we're on the wrong spot. We're looking at in between. We can see that here we're shading in between these two numbers. We have endpoints. So what happens here is, what's happened is we're going from -2 to the right, which is all my x's greater than or equal to -2, but also my solution has to include from 5 to -infinity, so all my x's less than 5. There's a hole here, so we don't include it. There's an open circle there. So the reason our answer here is in between there is because we're looking for the overlap. When we're talking about and, it has to work for both inequalities. So again, we're looking for the overlap. Again, we're looking for the sandwich. We have endpoints here. So the interval notation is a lot easier. Our interval notation is just going to be the two endpoints. Our -2, we include it, so we use a bracket. The -5 is open circle, so we don't include it. So with our sandwich or our and type, our interval notation is just the endpoints and everything in between, and then just be aware of if we're including or not including a specific value. So rewriting and inequalities, so instead of writing x greater than or equal to -2 and x's are less than 5, we can do the condensed form. And this is where we put that x sandwiched in the middle. We have our endpoints, -2 and 5, and we can only use less than and less than or equal to symbols when we're doing this. So we can see here, the symbol is opening towards the x, and it's pointing to the -2. So when I'm rewriting this over here, I want it to point to the -2. Notice how it's now a less than. And then my x also needs to be less than 5. So now we have a sandwiched, condensed form of our and inequality. So to solve our and inequalities, again, just solve them separately, and then we're graphing. So we're going to subtract 3. 2x is greater than -12. Divide by 2, we get x is greater than -6. And then here we add 2 to both sides. We get 8x is less than 32. Divide both sides by 8, we get x is less than 4. So when I graph this, I want my x's to be greater than -6. So starting at -6 here, we're going to go to the right. And the x's also need to be less than 4. So the overlap is from -6 to 4 and in between. So my interval notation, I'm going to put my two endpoints. I don't include the -6 and I don't include the 4. You can also rewrite this as a sandwich. We always go from smallest to largest number, and then we just put our inequalities here. less than, and then that one's going to be a less than as well. Now, if we have condensed, the way this one's condensed here, we have that inequality, we have this expression in the middle. The way we're going to solve this is we're just going to work from the inside out. So I'm actually going to subtract this 4 to the outside 2. That leaves me with 0 less than 3p less than 15. Then we divide both sides by 3. That leaves me with 0 less than p less than 5. So we automatically get it in that sandwich. So it's a lot easier to actually graph when it's in this form. I can see my endpoints 0 and 5, which we don't include because they're less than, not less than or equal to. And then we shade in between. My interval notation, again, we use those 2 endpoints. And they're open circles, so we have parentheses on both of those. So when we're looking at absolute value inequalities, we have 2 cases here. We have when we're looking at greater than or equal to absolute values, and then we have less than and less than or equal to. So just like before, remember that we have 2 cases. We have one when we keep it the same, x and then 7, and one when we switch the other side. Well, if we keep it and then we switch, we negate or we make the other side of the inequality negative, we also have to flip that symbol. So when I graph this, I want my x's greater than or equal to 7. So that's going to be right here to the right. And less than or equal to negative 7. So we include it, and then to the left, we have an OR statement. So my interval notation goes from negative infinity to negative 7, included, in union with 7 to positive infinity. For the less than, again, if we keep it, there's our first possible solution, but then remember that we have 2 possibilities. We also went in, there's a negative inside the absolute value, but if we make that negative, we got to flip that symbol too. So when we graph this, my x's need to be less than 4, less than or equal to 4, so we have a closed circle, and then greater than or equal to negative 4, so closed circle. So my overlap is between those 2 values. My interval notation will be from negative 4 to 4, and both of these are included. So what does that mean? Well, if we think about what we just did a little while ago, absolute value inequalities are just compound inequalities. They are compound inequalities as well. So it's the same case as we did up here. We're going to be having and or statements. So whenever we see greater than or equal to, those are going to be or statements. When we see less than or equal to, this is going to be our and statements. So just like with absolute values, we have to first isolate the absolute value expression. So make sure we leave that alone, add, subtract, multiply, whatever we need to do to make sure that the absolute value symbols are by themselves. And then the 2 cases that we create, it's what we call the KISS method. So we keep it the same for the first case. When we switch, we switch the symbol and we switch the sign of that other side of the inequality. So just like before. So when we look at problem number 1 here, and then of course solve both inequalities and then graph, and then we're going to put an interval notation. So looking at number 1 here, isolate the absolute value. It's already by itself. There's nothing in front of it, nothing after it. So we are going to make our two cases. So my first case, we're going to keep everything the same. So we have x plus 6 is less than 7. And then for case 2, we're going to switch and switch. So we have our x plus 6, then we're going to switch that inequality symbol. I'll put that in a different color. And we would go from a positive 7 to a negative 7. So now when I solve each one, we subtract 6 to the side here. We have x is greater than 1. When I subtract 6 on this side, we have x is less than negative 13. And I can see right here by my inequality, since it's greater than, it's going to be an or statement if I graph this correctly. So we want my x's to be greater than 1. So at 1 here, open circle, greater than 1. And then less than negative 13. So again, open circle, shade to the left. That is an or statement. Or statements go in opposite directions. So my interval notation will be from negative infinity to negative 13, not included, in union with 1 to positive infinity. And again, that 1 is not included. Number 2. Again, step 1, isolate the absolute value expression. It's already isolated for us. So we're going to go ahead and do our two cases. We're going to keep everything for the first one. So our inside stays the same, and then we're going to keep that inequality and keep the 19. Then over here, we're going to switch. So we write in our inequality, what's inside the inequality, the absolute value, and then we're going to switch that less than to a greater than and switch that 19 to a negative 19. And now we just solve. Add 3 to both sides. We get 2v is less than 22. Divide both sides by 2. We get v is less than 11. For my other case, we add 3 to both sides. We get negative 16. Divide both sides by 2. We get v is greater than negative 8. Now, according to this, since it's a less than, it should be an and statement. So we should have a sandwich here. We should have an overlap. Let's try it. We want our v's to be less than 11. So 11 is going to be right here, less than 11. And then our v's are going to be also greater than negative 8. So greater than negative 8, all of that. So my overlap is from negative 8 to 11. This is where it overlaps. So our interval notation, again, is nice and easy. We look at our endpoints, negative 8 to 11. According to our drawing and to our inequalities, we don't include any of those points. All right, number 3, it already has the absolute value symbol or the expression already isolated. So now we're just going to do our two cases. So we're going to keep the first. And then we're going to switch. So negative 5 plus k over 3, switch and switch. We made it a pause. We made it from a greater than or equal to a less than or equal, and my 1 goes to a negative 1. And now we solve. So I'm going to add 5 to this side. We get k over 3 is greater than or equal to 6. Multiply both sides by 3. We get k is greater than or equal to 18. Add 5 to both sides here. We get k over 3 is less than or equal to 4. Multiply both sides by 3. We get k is less than or equal to 12. And again, if we look at our inequality, that is greater than or equal to, which means it should be an or statement. So that should look like number 1, where they go in opposite directions. So k's must be greater than or equal to 18. So we include the 18 and go to the right. and k is less than or equal to 12. So solutions are in one or the other part of that graph. So for my interval notation, we go from negative infinity to 12 included in union with 18 included to infinity. All right, last one we're going to look at, again, the absolute value is isolated, so we're just going to create our two cases. Keep everything the same with our first case. And then for the second case, we're going to switch the inequality and switch the sign of the other side. When we solve here, we subtract 7. We get negative 4n. It's less than or equal to 20. Now be careful here. We are dividing both sides by a negative number. So we need to flip that sign here, that symbol. That becomes n greater than or equal to negative 5. Subtract 7 over here. We get negative 4n is greater than or equal to negative 34. And again, we're dividing by a negative number. So we need to flip that symbol. I'm going to leave that as a decimal just because it's easier to graph a decimal on a number line than a fraction. So we want, according to this is less than or equal, which is going to be an and statement, so it should be a sandwich. So let's see what it says. We want our n's to be greater than or equal to negative 5. And then we want our n's to be less than or equal to 8.5. So we're going to include it here and then go this way. So my overlap is in between those two endpoints. So for interval notation, we're going from negative 5 included to 8.5 also included. We'll be doing more practice in class, somewhere we might have to do a little bit of work before we create our two cases so we can work on isolating the absolute value expression.